My talk is, as Reese said, a talk in the philosophy of mathematics. And so I'm going to talk about Grothendieck's work as a case study, illustrating some points on the ontology of mathematics, perhaps a little bit like Elaine's talk yesterday, but not at all like something different. So more specifically, I'm going to talk about mathematics and fiction, and I am going to compare mathematics and fiction and ask whether mathematics is like fiction. And maybe the answer to that question is obvious to you now after having heard all these things about Grothendieck, but I will try to say it anyway, or respond to the question anyway. And so one motivation for asking these questions comes from the philosophy of mathematics when asking the question about the nature of mathematical objects, whether mathematical objects are created by us or whether we think they exist independently of us, that is, whether we are realists or anti-realists. But then if we want to talk about truth in mathematics, stating that certain statements in mathematics are true, there are philosophical arguments saying that we need to believe that mathematical entities exist independently of us. But then rejecting that this is the only possibility, fictionalists have suggested a way to talk about truth in mathematics without stating that the discourse is about independently abstract objects. So their solution is to say that we talk about truth in mathematics as we talk about truth in stories or in fictional pieces of work. So so we can talk about mathematics as true in the story of mathematics. So, for example, or you probably have your favorite piece of fictional work. But so if I were to say that in the story of Sherlock Holmes, his good friend, doctor friend's name is Moriarty, you would certainly object. And then I would correct myself and say, no, his name is Watson. Then you would agree that this is true in the story of Sherlock Holmes, even though these characters do not exist. And but then taking this option requires that mathematics is like fiction in certain ways. And so this is what I'm going to talk about in this talk. So I'm going to say that even though there appear to be superficial likenesses between mathematics and fiction, if one scratches the surface, there are fundamental differences. And the main focus of this talk is on the multifaceted role that relations play in mathematics. And I'm going to illustrate this by looking at the case study that I mentioned in the beginning, by looking into the history of K-theory, and more particularly, I'm going to zoom in on Grothendieck's work before this, when he introduced the first K-group. So a little bit about the content of this talk. I'm going to, first there's some more introductory slides, and then I'm going to mention some set similarities between mathematics and fiction. And I'm also going to list some set general differences between mathematics and fiction. And I have a list of some mentioned differences. I will not go through them because my main focus will be on the role that relations play in mathematics. And as I say here, and I will illustrate this by this case study on the history of K-theory. And then there will be some that will take most of this talk. And then I'm going to focus on the interconnections in mathematics, and there will be some concluding remarks in the end, and some questions, time for questions and comments. So mathematics has been compared with fiction since both depend on the same human ability that we can postulate objects and tell stories and reason about them. It's kind of perhaps the same view that emerged from Elaine's talk yesterday, this as if, and perhaps not, but we can come back to that. But I claim that the way that mathematical objects are postulated is quite different from how fictional characters come into being, and that relations play a much more fundamental role in mathematics. And when I talk about relations in mathematics, I do not only talk about relations of these individual structures that we might talk about, like the groups or the natural numbers, but I also talk about relations more globally, the relations that exist, for example, between a group and the natural numbers, and even between different fields in mathematics. And the point, also one point is that the mathematical universe is tied together in multiple ways. So you could have this idea that there are these elementary basic mathematics at the bottom level that we introduce in order to say something about the real world, perhaps observe representations of this physical world, modeling, and then we build on top of this elementary level, making more abstract theories. But then as we go along, we also find interconnections between these different fields. And then rather than talking about truth in mathematics, I prefer to talk about the reality of mathematics, also based on this picture of interconnections. And this interconnections offers a way to state why mathematics is real. I say that it's pragmatically real because it has ties to this physical reality. It can tell us about this physical reality. And mathematics is not real or true because we can formulate internally consistent stories about certain postulated objects, as we do in fiction. And the final, also introductory slide, some things about, or facts, I don't know if there are facts or not, characteristics of mathematics. So one main characterizing feature of mathematics, of course, is reasoning. So we formulate hypotheses from which to reason, and that means that mathematics, module mathematics has two parts. One is once we have this hypothesis, and I take a hypothesis in the sense of an assumption or supposition, you derive what follows from this hypothesis. And the second part, of course, consists of formulating the hypothesis from which to reason. And the case study that I'm on Grothendieck's work is about this part, finding the hypothesis or finding new mathematics, formulating new mathematics. It's also common today to say that contemporary mathematics is the study of relations between objects rather than the objects themselves, that is, it studies structures. So I think this is not very controversial to say. But also, moreover, there are these global relations, the interconnections that play a role in mathematical activities when reasoning or introducing new objects. And these do not only rely on relations of the considered structures equally important, as I said before, are the more global interconnections in mathematics. They also play a role when introducing or developing mathematics. And so similarities between mathematics and fiction. So I already said this, that they are said to both rely on the same human ability. We're able to introduce objects, postulate objects, and reason as if we create objects and tell stories about them. And you might also say that describing relations is as important to fiction or stories as it is in mathematics. So we introduce characters, places, things, but in order for the story to work, you also need to say how these relate. So you have to, if there are people involved, you need to say whether they're relatives, they could be married to, they could love each other, or if you have a place and a person, you could say that that person lives in a certain place, and so on. But then for the most part, these relations are concrete relations, whereas in mathematics, perhaps you could have something like concrete relations in the basic math, but very quickly they would become much more abstract, like transitive as asymmetric relations. And I also said that I would list a number of differences between mathematics and fiction before I even start talking about this role that relations play in mathematics. And here is a list. Some of them, perhaps all of them, are inspired from reading 2 papers by Robert Thomas, the editor of Philosophia Mathematica. He has 2 very long papers, from 2000 and 2002. The one is about ask the question whether mathematics is like fiction, and the second one is about whether mathematics is analogous to mathematics. And Thomas rejects both. He thinks it's neither like nor analogous to fiction. But I won't go through them. You probably just skim them yourself. So my focus here is the role of relations in mathematics. And so coming now to the history of K-theory. I don't know, you might know about this history and all already, but I'm going to go through it quickly. So K-theory was developed, I don't know if I can get this to disappear, by Sir Michael Aitia and Friedrich Hirzebruch in the late 1950s. They formulated K-theory, which consists of a series of groups in topology. Later, K-theory was also developed in algebra and in persistent algebras, and extended and generalized in all sorts of ways. And their work was based on the work of Grothendieck, who introduced the first K-group in connection with a generalization of this Riemann-Roch theorem of Riemann-Roch, and we already heard mentioned this yesterday. And so, as the name suggests, this comes from Riemann, who in 1857, after having formulated his surfaces that is later named after him, asked the question: how many complex valued functions can be defined on such surface with geometric genus G and with poles at a number of given points. And Riemann was able to establish the existence of such functions. And then later his student, Gustav Roch, was able to determine the precise number of how many different such functions was possible to define. And today we would say how many linear independent functions are possible to define. And then this is a theorem for complex one-dimensional surfaces, that is curves. And so the question became whether it's possible to generalize this theorem to arbitrary n-dimensional manifolds. And this turned out not to be so easy. So one challenge was how to generalize this geometric genus G, which then became the arithmetical genus, which was introduced by Severi. I don't know if anybody had this idea before, the Italian geometrist Severi, but he proposed an expression which was an alternating sum of dimensions of some n forms, and he actually had 3 different expressions for arithmetical genus, and it was later proved using K-theory that these 3 were indeed identical. And but then in 1956, Hirzebruch was able to formulate this theorem for n-dimensional manifolds. So his version is in topology. He considers algebraic manifolds, and there are vector bundles defined over them. And then the year after, Grothendieck formulates his generalization, now in algebraic geometry, where basic objects, as we already know, are algebraic varieties with sheaves defined over them. So now I'm just going to focus on Grothendieck's introduction of the K group, how he defined it and why, if he defined it the way he did in the Romanian. And perhaps first just a little bit of background for Grothendieck's version. So we heard most of this yesterday, so I'm going to say some of it quickly. So Grothendieck was born the 28th of March, 1928, had a difficult childhood. And after killing functional analysis, as we also learned yesterday, he became interested in algebraic geometry, where Mazur became one of his most important collaborators. And listing also some background, there's the Hooker paper that Jean-Jacques told us about yesterday. I'm also going to mention just a few of the things that Jean-Jacques told us in a minute, as some details from the case. And then, of course, so what is interesting here is, of course, his that he introduces homology with coefficients in a sheaf, and more importantly, that he was able to formulate the conditions that made this possible, introducing an abelian category. And of course, another thing that is interesting for a background for Grothendieck's version of Riemann-Roch is the theorem formulated by Hirzebruch. And then it's also said that Grothendieck, that he had this extreme taste for generality, always going for the most general result possible. And this resonates well with ideas of Bourbaki. And probably Grothendieck had this taste before he met the members of Bourbaki when he came to Paris and later Nancy. And we also heard a lot about Grothendieck and his relation with Bourbaki yesterday in Jean-Pierre's talk. And of course, we also learned yesterday that the necessity of using categories in Grothendieck's work. And so Grothendieck's theorem of Riemann-Roch is published in the paper Le Théorème de Riemann-Roch, and it's written by Armand Porel and Jean-Pierre Piasser, and not himself. And the article that they have written is based on a seminar that was held in Princeton in 1957. But there is a version of Grothendieck's Riemann-Roch published later in one of his SGAs. And before going, I'm just showing you Hirzebruch's version, or part of it. So here we are considering these n-dimensional algebraic manifolds, and we have vector bundles defined over this algebraic manifold, some fibers, and then it's possible to define the cohomology groups and formulate the Euler-Poincaré characteristic, which is, by the way, generalization of this arithmetic genus that was introduced by Sibiri. And this, the theorem says that this alternating sum of the dimensions of the cohomology groups can be expressed as a polynomial in the Chern classes of V and W. And so what is interesting here, and what I'm going to focus on, is this expression, because it's when generalizing this expression that the K group appears. So, as I say here, And so in Grothendieck's version, so being an algebraic geometry, he considers algebraic varieties and not n-dimensional algebraic manifolds. And instead of vector bundles defined over them, there are defined coherent sheaf over X. And also it's a relative version, perhaps inspired from the category theoretic way of seeing things. So instead of just having an algebraic variety with sheaves defined over it, he considers the situation where we have a map between two different algebraic varieties and there is defined the sheaf over X. And as I said, the K group is introduced when generalizing this expression. And so what he wanted to do was to define a homomorphism here, F shriek, from sheaves defined over X to sheaves defined over Y that somehow reduces to this expression. And so given a map from one algebraic variety to another algebraic variety, it is possible to construct a whole series of sheaves over Y that actually reduces to this cohomology group when Y is a point. They're called higher direct images of the sheaf F, and they're written in this way. And Jean-Jacques showed us how we get them yesterday, just repeating it here. So first, you construct a pre-sheaf over Y using the sheaf already defined over X. So for each open subset of Y, take the pre-image and then you take the section of the sheaf over F corresponding to this subset. And this is an abelian group. And then you take the limit and you have a sheaf over Y. This is the direct image. And then for each short exact sequence of sheaves, it was known at the time that there exists a whole sequence of sheaves here. And it's also possible, since we're dealing with coherent sheaves, to show that at a certain point, these objects here, they vanish. So we will have a long exact sequence. And so now having all these higher direct images that reduces to the cohomology groups, the obvious expression of this homomorphism is of course to form the alternating sum of these higher direct images. But then having a map from sheaves over X to sheaves over Y does not allow us to formulate this expression because it's an alternating sum of sheaves, and an alternating sum of sheaves is not itself a sheaf. So we need to do something. There is a resistance in the mathematical context. And so to fulfill these two requirements, that this function, F shriek, the expressional function, reduces to the alternating sum of homology groups, and that it is a homomorphism, Grothendieck decided to introduce this quotient, the K group, where the top here is the free abelian group generated by sheaves over X, and over this it's possible to form the alternating sum, so check, but it doesn't make the function or the morphism a homomorphism. In order to do this, he mods this subgroup, mods out with this, and Q of X is generated by the expression F minus F prime minus F double prime whenever we have a short exact sequence like this. And this turns the function F shriek into a homomorphism in the following way. So if we have this identity in K of X, F shriek should fulfill this, being a homomorphism. And if this holds, then we have a short exact sequence of these sheaves. And then, as I showed you in previous slides, we have this long exact sequence of the higher direct images. And then there is a theorem stating if we have a long exact sequence of these sheaves, then the sum of them is equal to the alternating sum of them is equal to 0, which are written here in a modified form. So it follows directly that we have this expression, and then moving things around here, we see that this is exactly what I've stated here. So you get that the function is a homomorphism. Yes, so that completes Grothendieck's work, his introduction of the K group to being able to formulate this part of the theorem. So now I return to the part of my talk that relates it to fiction, whether mathematics is like fiction, and the role that relations or interconnections play in mathematics. So I haven't said anything about it explicitly in the talk, but yeah. So, and previous talks already mentioned some of Grothendieck's unifying concepts, his tropices and the schemes, for example. Today, this morning, we had a talk about motifs that also make bridges and unifies. And we're also going to have a talk later this week by Carmelo, who I found the title of this paper that both have the idea that there is some kind of unifying thing going on, but also the bridge. That first we have the interconnection, and then we have the bridge. And this is not only true the exploitation of the interconnections to making unifications in the work of Grothendieck. It occurs in mathematics in general. I just listed some examples here, and you can read them and perhaps agree that this is something that goes on in mathematics. Mathematics is replete with interconnections that we exploit. And apparently, interconnections are so important to mathematics that mathematicians have found a way to classify them. So this is taken from a recent talk by Mazur, who is also was a friend of Grothendieck, where he classifies these different interconnections, and the classification is in terms of how formal the link or the interconnection is. So first there are ties, and a tie is an entity or object that links different types of mathematical domains. And as example, he mentioned the Bernoulli numbers, which connects analysis, number theory, homotopy theory, etc. We might think about K-theory in this way, since we have the K groups that are possible to define from many different areas. As I said, we have topological K-theory, algebraic K-theory, and K-theory for star algebras, bearing in mind that it's certainly not the same K groups. It's similar construction, but not the same groups. The next is analogy. This is where we don't have a formal relation, but there is some perceived similarities between so for example, we have the fundamental theorem of arithmetic, where the idea is that for any integer we can write that uniquely as a product of primes. So we have this basic building block from which we can recover all other entities of that set or collection. And that idea has inspired many other parts of mathematics. So Mazur mentions that it's used in knot theory, finding certain basic knots from which you can, so you can decompose any knot into these basic components. It occurs, for example, in the finite abelian groups, where you can decompose any group into finite cyclic groups, and so on. It occurs many different places. There are the links, and when we have a link, there is a formal relation between two different structures or areas of mathematics. So there is a formally expressed relation between two fields. And Mazur mentioned the Langlands program and the role that duals play. And finally, there's the bridge. This is where the established links is used systematically in order to formulate a new field that exploits this link. So in this way, we have formed analytic geometry, geometric algebra, and so on, many different fields. And coming back to the case on K-theory, because I see there are all these different types of interrelations also in the case study. So we have this global analogy. There's some perceived similarity. We have first the Riemann-Roch theorem. We have Hirzebruch-Riemann-Roch, and there is some kind of similar situation. We have some basic objects, the algebraic manifolds, and some structure defined over them. And then we have in algebraic geometry, we also have this basic object, the algebraic varieties, and some structure defined over them. So Grothendieck got the idea that it would be possible to transfer results formulated in one setting to the other setting. But there's no formal relation set up. It's a perceived analogy at play. There are also links that certain formal relations are being formulated and exploited. So there are many examples of this, and we do it all the time in mathematics. So this is just one example. So in this paper, for example, this theorem 2, I think it is, they perform the same construction, K-group construction on fiber spaces and prove that there is a bijective correspondence, and this correspondence can then be used to transfer properties of this one into properties of the K-group. And the Riemann-Roch theorems themselves establish links between various or correspondences between various mathematical objects. So in Hirzebruch, Riemann-Roch, there established correspondence between the homology groups and the top homology, for example. And finally, there, besides these links and analogies, the interconnections, there are also considerations of internal coherence and just the justification of the introduction. So you cannot just introduce an object at your will, that there are certain resistance to the mathematical context that you are working in. So you cannot just introduce this function f shriek and say that it has the properties we want it to have, but we need to do something. We need to, for example, form the quotient, introduce the K-group in order for things to work. So coming now to the final concluding remarks. So in addition to present one of Grothendieck's many implicit contributions, talk concern what can be said about the reality of mathematical entities, or in particular in relation to fiction versus mathematics. And I've tried to show, I guess, no, that yes, that postulation or introduction of mathematical objects governed both by global relations, the analogies, perceived similarities that motivates the generalizations, as well as the internal constraints. We cannot just introduce whatever we want into mathematics. Yeah, here comes what I just said. We cannot create mathematical objects at will. We perceive analogies that motivate, and then when the right concepts have been introduced, the results fall out almost like magic. But that hides all the work that you have to do before getting to the right concepts. But even though I use this word magic, could have indicated some kind of fictional image, I claim that mathematics is not like fiction. And a main difference that I hope to have convinced you of is the extent that relations play systematic roles in the development of mathematics. And that's it.